All right, guys. So let's get started. Good evening. Well, 2 weeks ago, so we introduced the concept of convolution and filters. Well, by the way, we will have a makeup class during the revision days. Revision days should be from November 30 to December 3 or 4th. Okay, so we're gonna have a makeup class in one of these few days. Okay, so well, we have introduced a variety of filters. Remember? So what can a filter do? A filter is typically represented as a matrix, right? So we have seen filters that can be used for smoothing. And what else? Smoothing, shifting, and sharpening effect. Okay. Well, in this class, we're gonna introduce more filters, but those filters can be used for identify edges, edge detection. Okay, so we are going to see filters in the form of matrices, but they are very versatile. They can be expressed in many other ways and accomplish different tasks. Okay, so in filter and convolution, one thing I would like to mention is that when you do convolution, you need to flip the filter before performing the calculations. Okay, it's because convolution is defined in this way, and if you want to know why, if you want to understand why convolution is defined as a flipping, is defined in this way, that you should flip the filter first and then do convolution. You could go to this block. Okay, so mathematically it's defined in this way. Therefore, when we do actual convolution, we need to flip the filter first and then perform the calculations. Okay, so in the following, when we introduce edge filters, we need to keep this in mind. Edge detection, edge filters. So we're gonna see, for example, this kind of filters, Sobel operators. Okay, of course, you know, these filters are symmetric. Symmetric with respect to the y-axis, and also symmetric with respect to the x-axis. So it doesn't matter whether you flip it or not. Okay, but we are also going to see filters, for example, this kind of filters. Then you need to do the flipping before the calculation. Okay, so anyway, in this class, we're going to learn some filters for edge detection. Why edges are important? So here you can see some paintings and line drawings by a 7-year-old. And C is a Chinese painting, ink painting. And A is a cave painting. And this is an aerial photograph. And common to them are the edge information contained in these paintings or line drawings. So edges are important because edges contain structural, right? Structural and semantic information about images and the scenes. Where do edges occur? Edges usually occur at what? At the boundary. At the boundary of an image. So this is where an edge occur at the boundary of the image regions. So edge occur at the boundary of image regions. And edges represent significant changes, right? Significant changes in image intensity. So to show the importance of edge detection, we want to show you a famous experiment performed by Hubel and Wiesel, which wins them the Nobel Prize.
The researchers actually listened in to individual nerve cells firing in the anesthetized cat as they presented it with different visual images.
When we started working, Torsten and I, in the late 50s, we set up our first experiments, and they didn't go well because at the beginning we couldn't make the cells fire at all. We'd shine lights all over the screen.
So they perform an experiment.
Researchers actually listened in to individual nerve cells firing in the anesthetized cat as they
Well, there's a cat here. See, there's a cat here.
Presented it with different visual images.
When we started working, Torsten and I, in the late 50s, we set up our first experiments, and they didn't go well because at the beginning we couldn't make the cells fire at all.
So there's a cat face here, see? There's a cat here, okay?
We'd shine lights all over the screen, and nothing seemed to work. And rather by accident, one day, we were shining small spots, either white spots or black spots, onto the screen. And we found that the black dot seemed to be working in a way.
So they're shining these small spots, either white or black spots on the screen, trying to see whether the cat responds to such stimuli.
And we found that the black dot seemed to be working.
The black dot seemed to be working
in a way that at first we couldn't understand.
But actually, it is the boundary of the slice. So actually, the cat is a response to this line instead of the black dots.
And until we found that it was the process of slipping the piece of glass into the projector, which swept a line, a very faint, precise, narrow line across the retina. And every time we did that, we'd get a response.
The researchers actually listened in to individual nerve cells firing in the anesthetized cat as they presented it with different visual images.
When we started working, Torsten and I, in the late 50s, we set up our first experiments.
So this is the experiment in the late 50s, like 70 years ago.
And they didn't go well because at the beginning we couldn't make the cells fire at all.
So this is a cat. They want to see whether the cat responds to some stimulus.
Shine lights all over the screen, and nothing seemed to work. And rather by accident, one day, we were shining small spots, either white spots or black spots, onto the screen. And we found that the black dot seemed to be working in a way that at first we couldn't understand until we found that it was the process of slipping the piece of glass into the projector, which swept a line, a very faint, precise, narrow line across the retina. And every time we did that, we'd get a response.
The research.
So, the discovery that they are cells specialized in the cat's brain or in the brain of mammals. Their cells specialized for detecting lines. And this won them this is the cat's brain. Okay, so it responds significantly, fiercely to the line. Okay, so this discovery won them the Nobel Prize, and this lays the foundation of neuroscience, as well as, CNN, convolutional neural networks, which are the invention of CNN is also inspired by these discoveries. Okay, so edges. Why edges are important? Why edges are important? Because edges encode. Edges are fundamental building blocks of vision. Edges encode the semantic and the structural information. And edges are foundations. Edge map. Edge map. What is an edge map? For example, this is an edge map. Okay, so edge maps are foundations for advanced vision tasks such as segmentation, recognition, scene understanding. Okay, so edge map is a foundation for many complex vision tasks. That's why we want to do edge detection. We want to be able to extract edges which represent semantic and structural shape information of the image, and it will help us to understand the content of the image. Okay, now before we introducing edge detection algorithm, let's look at another experiment. This is another study in neuroscience, and you can see this study is published in PNAS, a famous journal. So in this study, the participants are presented with two groups of images. One group is the set of real photographs, and the other group is the corresponding line drawings. Okay, so they present the two groups of images to the participants and record their fMRI data. These are the fMRI data. Okay, and then they train an algorithm to classify to decode the category of the images from the fMRI data. Okay, and here the red one represents the result of the classification result, the result predicting the categories using the fMRI data of the line drawings. And the red one presents the results of the prediction using real photographs. Okay, so you can see from the results that despite the huge difference between the real photographs and the line drawings, well, they are quite different. Okay, the two groups, they are very different. They are different in color, statistics, in many ways. Okay, however, the algorithm is equally capable of telling which category the image belongs to. They are equally capable of guessing the category of the images for the real photographs. I mean, from the fMRI activity. When the participants see the real photographs and the fMRI activity when they see the line drawings. Okay, the algorithms were equally capable of guessing image categories, regardless of it is fMRI, regardless of it is the real photographs or regardless of whether it's the response, the activations of real photographs or the line drawings. And this shows that our brain responds similarly. Our brain activity, our brain activities respond similarly to real photos and line drawings. Okay, and this again shows that the line drawings contain significant amount of semantic information. So it actually contains a lot of the semantic information. So that's why we want to do edge detection. We want to extract the edge information from the images. Okay, and this few slides shows that why do we care about edges? It can be used for extract information, recognize objects, and we have explained that. But it can also recover geometric and viewpoint information. Okay, help us to understand the geometry of the object. And for these few slides, it shows up the how edges are created due to surface normal discontinuity, depth discontinuity, as well as color discontinuity. So as we explain, edges represent a significant change, and the significant change often occurred between the boundaries of regions, therefore discontinuity. Okay, often occur at the boundaries of different regions. Anyway, okay. So this is an ideal result. This is the ideal result of edge detection, but in reality, well, we often get a result like this, and you can see the edges, they are not continuous. They are not perfect. So we're going to see how to do edge detection in the following.
So let's look at edge detection with a simple example. I'm going to give you my usual simple image. Let's use this as an example and see what we can do with it. So the basic idea of edge detection is we want to look for a neighborhood with strong signs of change. So let's, for example, look at this pixel or this neighborhood of 1 and look at it with respect to the other pixels around it. How much is the change from here to there? How much is the change from here to here? And also basically just in that neighborhood of these pixels here, figure out, oh, is there a big discontinuity here? And of course, there is a significant discontinuity, 12 intensity to 90. We can basically start looking at that one by one throughout the whole image.
So remember, when we look for edges, we want to look for significant change or significant discontinuity. So from 12 to 90, there's an edge here because there's a significant change in the pixel values. Okay, but instead from 12 to 10, this way, the change is not so significant. So we might not want to, so this may not represent a significant edge.
So of course, the same when I look at this and I compare it with this, there's a discontinuity, a significant one between these two. However, not much so between 90 and 89. Looking at this pixel here, I would also have the same comparison, much more discontinuity here. Of course, I didn't go down all the way here, but if you notice 89, 86, 87, 82 were somewhat similar. Not exactly the same. I mean, there is discontinuity, just not a significant one. But between 12 and 88, much more. Again, we can keep coming down this way. And 9 and 10 have discontinuity. 15 and 12 have discontinuity, but small. So when I hit 12, you basically know there's a significant discontinuity here. And also between 12 and 84. So this process, basically, as I scan through an image, I will be looking for each and every pixel and look in the neighborhood, the four connected next to it itself, and say, okay, do I need to put something between those pixels to create an edge? And I can just go through the whole process and see how this looks for this instance. And you can basically see that, of course, just by looking at discontinuities between different types of things, we can create this simple line which separates out this part of the image with that one, or basically points out that there is a discontinuity between it. Here is another way of looking at it. Basically, now I've just given those gray values, and now I can see the edge between the two. It becomes much more clearer this way also.
Yeah,
so as we do this, we have to think about.
So if you plot the actual value, actual intensity value, you can observe there's a significant discontinuity. Okay, represented by the red edges, and these are the edges we're looking for.
About various things. What is the size of the neighborhood? I started off with basically the assumption that the neighborhood size, which I've always referred to, was 1 because I looked at it with respect to that. Then also, what metric represents a change? And in this case, we looked at saying is, well, let's not basically think there are different if the pixel intensity is different by 3. But if it's several orders of, in this case, of course, almost 78, we will put that as an edge. Or in this case, again, about 76. So all of those variations are much larger. So we basically came up with some sort of a threshold and defined that as where we want to actually look for those changes. So if there was with certain amounts, if it was above it or not, we would actually look for that discontinuity. Of course, there is discontinuity, much smaller one between each and every pixel, but we will just be looking for larger ones. So
okay, so that's how we do edge detection. We compare nearby pixels. We compare the intensity of neighboring pixels. But how do we define neighbors? Well, in this case, the neighborhood is said to be 1. So meaning that we might want to consider the difference between the current pixel, which is 90, and the pixel to its left. Okay? Or we may consider the difference between the current pixel, which is 90, and the pixel to its right. Okay? If the current pixel is 12, and we may also consider its difference between the pixel to its right. So it depends on how you define the neighborhood, how you select the pixel for comparing. We can also compare, the difference between the left pixel. If the current pixel is 90, we can also compare the differences between its right pixel, which is 89, and its left pixel, which is 12. Okay, it depends on these are the design choices. It depends on how you calculate the differences in this neighborhood. And what represents a significant change? What represents a significant change? You need to set some threshold. Okay? If the changes are too small, like this, if the changes are within, the differences are just 2 or 3 or 4 or 5, then these changes may not represent a significant edge. And you shouldn't consider them as an edge pixel. Okay? So basically, there are 2 issues to consider. One is how you calculate the differences. And what metric? You need to set up the threshold to only preserve the significant edges. Okay, so the idea for edge detection is really simple. First of all, we draw an intensity function. The intensity function here represented by the red line. This red line, the intensity function for this red line is represented as this function. You can see at the beginning, the function, this is function f, and this is the index of the pixel. Okay, for example. So initially, at the beginning, the function value is at around 255. And then for the function value within this range, its value is 0. Okay, then it go up again to be 255. So where are the edges? Apparently, the edges are here and here. Okay, so edges occur when there's a significant change. And how can we capture such changes? Remember, we compute the differences between neighboring pixels. And this difference, such differences is represented by the first derivative. The first derivative mathematically is just the difference between neighboring pixels. Okay, between neighboring pixels. If this is a function fx, the first derivative is just fx minus fs minus 1. Or you can define first derivatives in other forms, but in other similar forms. Then let's look at the first derivatives. This is the graph for fx, the graph for the derivative of fs. Okay, and you can see they are two peaks. Well, this is a high peak, and this is at the negative value. The first derivatives, if we take the absolute value, then we have 2 peaks. One here, the other one is here. And the peaks, or the extremas, correspond to the edges. Okay, the position where the extrema in derivatives corresponding to the extrema of the derivatives represents the edge position. Edge occurs at the extrema of the derivatives. Okay, as simple as that. Now we're going to define image gradients and use them to calculate edges. This is the derivative for real function. So we have, suppose f is a real function with only one variable x. Okay, so this is the definition of derivatives. So let's recall how can we compute the first order derivative of this polynomial function. The polynomial function is just 2x plus 4x power 3. And this is the derivative for this sine function plus an exponential function. Okay, so that's the derivative for real functions. Then what about the derivative for images? You know, if fs is a real function, delta s can be arbitrarily small. Delta s can be arbitrarily small. And this represents the changes in the function value with respect to the changes of the input, right? Changes in the function value with respect to the changes in the input. But in terms of images, images are discrete signals. Images are discrete. So what is the smallest value of delta s can take in terms of image? In image, how do we define derivatives in images? What is the smallest value delta s can take? In real function, delta x can be arbitrarily small, right? Real function, the derivative of a real function is the ratio, is the limitation of this ratio when delta s goes to 0. But images are discrete signals. So in terms of images, what is the smallest value that delta s can take? 1 is just 1, okay? So the image derivative is defined as what? Fs minus fx minus what? Delta x can only take 1, right? And delta s is 1. That's it. That's the derivative for images, or one-dimensional discrete derivative. Okay, so this is our image derivative, one-dimensional image derivative. And it's exactly the differences between two neighboring pixels. Okay, and like we said before, there are many other ways. There are multiple ways to define such derivatives. Okay, this is the typical way, and we call this backward filter. So it calculates the difference between the current pixel and the pixel to its left. Okay, and this one is called the forward filter. It calculates the difference of the current pixel and the pixel to its right. And this one is called the central filter because it calculates the difference between the pixel to its right and the pixel to its left. Okay, and if we express these discrete filters in terms of filters, it can be represented in correspondingly in this. Well, notice that how -1 goes to here instead of here because of the flipping. Because when you do calculation, you should flip the kernel, and after flipping, -1 just goes to here. Okay. So what I'm trying to say is, if you represent the backward filter, it should be represented in this way instead of this. Because this represents a convolutional filter. This one is a convolutional filter. And when we do the actual computation, this filter has to be flipped. And after flipping, it becomes like this. It becomes this. Okay? Okay. So backward filter, this is backward filter. And after flipping, it becomes this. So what it actually computes is fx minus fx minus 1. Clear? And similarly, for the forward filter is represented in this form. And after flipping, it becomes like this. It becomes like this. So what it actually computes is fx, this one, minus fx minus plus 1. Okay, so it is a little confusing because of flipping in convolution. Well, similarly, the central filter is represented in this way. Well, one is here, minus 1 is here, and after flipping, it becomes minus 1, 0, 1. Okay, so after flipping, the actual computation is fx minus fx minus 1. Okay. Okay, so just so you know, when we represent a filter in the form of convolution, we need to flip it first before we do the calculation. Okay. Well, now we have fx. Now we have fs and its first order derivative. Can you tell how the first order derivative is computed using the forward filter or backward filter or central filter? So how can we get this? How the derivative of fx is computed using forward filter or backward filter? You know, this is the backward filter. Backward filter is the subtraction subtracting the left pixel from the current pixel, while forward filter is subtracting the future pixel, the right pixel, from the current pixel. So how do we compute this? How do we obtain the derivative using backward or forward filter? Forward filter. Agree? You know, how do we get, well, how do we get 10 and how do we get 5? 5 is computed. 5 is obtained by subtracting 10 from 15, right? Right? And 10 is obtained for, perhaps let's pad a 0. Let's pad a 0 to the left of fs. Let's pad 0. So 10 is obtained by subtracting 0 from 10. And 5 is obtained by subtracting 10 from 15. And minus 5 is obtained by subtracting 15 from 10. And 0 is obtained by subtracting 10 from 10. And similarly, 15 is obtained by subtracting 10 from 25. Okay, so we keep doing this, and we obtain fx by subtracting by subtracting the left pixel from the current pixel, right? So this is obtained by backward filter. This is obtained by backward filter. 0 is obtained by 20 minus 20. 0 obtained by 20 minus 20. Minus 5 is obtained by 20 minus 25. Okay, so remember, we pad a 0 here, 0 padding, 0 padding. So the input, the length of the input is 8. The length of the output is also 8. So you can imagine that we need to do padding. So the output and the input are the length of the output and the input. They have the same length. Okay, we need to pad a 0 here. Okay. We have seen the cases of one variables where the function has only one variable x, one-dimensional function. But graphs, but images are 2 dimensions. Okay, so for for function with multiple variables, for example, an image function, it has 2 variables, x and y. Okay, then what do we do? Of course, we can take the derivatives in 2 directions. This is, we can take the derivatives in the x direction. This is fx. We can also take the derivatives in the y direction, and this is fy. Okay, so with 2 derivatives, now we have a vector, the gradient vector, consisting of the x derivatives and the y derivatives. All right, and when we have a vector, we can compute the gradient magnitude. The gradient magnitude is the is just the length of the vector. The length of the vector. The length of the vector. This is the L2 norm. Okay, the length of the vector is computed. This is a vector. This is a vector. Once we have a vector, we can compute its norm, the length of the vector. We can also compute the direction of the vector, where the direction of the vector is the arctangent of this ratio. Okay. Now let's take a look at the edge detection filters. Can you recognize this filter? What is this filter? What is this filter? Well, that filter turns out to be central filters. Okay, central filters. So each row of this filter is a central filter. Each row of this filter is a central filter. And there's a normalizing factor, 1/3. This is a normalizing factor because we have 3 rows of central filter. And this ratio, this scalar is to normalize the differences. Okay, so what does this filter do? What does central filter do? Central filter clearly is used for comparing the differences between pixel on its right and the pixel on its left. Okay. So clearly, this filter is responsible for comparing the differences of pixels, horizontal differences of 2 pixels, horizontal differences. Okay, so can you imagine this filter can be used for identifying what kind of edge? Say, you know, if there's a very large difference, if there's a large difference between these pixels and these pixels, if there's a very large difference between those pixels, it indicates that because there's a large difference between them, so there might be a significant edge here, right? Because there's a very large difference between them. So we can infer that this filter is responsible for detecting vertical edges. If there's an vertical edges, it means there's significant changes between these pixels, and this value will be large, because there's a significant differences. So this filter, if the value is large, it indicates there's a significant edge here, vertical edge. Okay. Well, similarly, what does this filter do? What about this filter? This filter is for identifying horizontal edges. Because it calculates the difference between the pixels above and the pixels below. Okay, horizontal edges. Okay. Well, without any calculation, what happens when we apply this filter? When we apply this filter computing the differences between what does this filter compute? It computes the differences between the pixel above and the pixel below, so it verifies the changes. This filter try to capture the changes along the vertical direction. Right? So can you, without doing any calculation, can you tell what happens when we apply this filter to this image? What can you observe for this image? Well, for this image, each column has the same value, indicating that there isn't any change along the vertical direction, right? There isn't any change along the vertical direction. Along the vertical direction, there's no change in pixel value. Therefore, if you apply this filter, and this filter, what this filter does is to calculate changes along the vertical direction, whereas there isn't any change along the vertical direction. Okay, so without doing any calculation, we can infer the result is just all 0. I mean, this part is 0. Okay, this part is 0 because the filter has a size. Okay, and if we apply the filter across the image, if we don't do any padding, we end up with this, the output is 3 by 3. And the output is just all 0 matrix because there's no changes along the vertical direction. Okay, let's take a 10 minutes break. Okay, let's continue. So what happens if we apply this filter? We call this filter Y derivative filter. We call this filter Y derivative filter because it measures the differences along the vertical direction. Okay, along the vertical direction, 1 minus 1. So the differences along the vertical direction. So we call this filter Y derivative filter. And we already know that because in this image, there isn't any vertical changes because each column has just the same value. So apparently, we do not need to do any calculation. And we can immediately infer the result of applying this filter. If, without any padding, the output will be a 3 by 3 matrix. Clear? Because the input is 5 by 5 and the filter is 3 by 3. 3 by 3. So the output is also 3 by 3. And we can immediately see the output is a 3 by 3 or 0 matrix. Okay, clear? Now let's try another filter. And we call this filter X derivative filter. X derivative filter. Okay, and notice that just like the moving average filter, both the Y derivative and the X derivative filter, there is a normalizing factor. Okay, the normalizing factor for the moving average filter, the normalizing factor is 1/9. But here, the normalizing factor is 1/3 because we are calculating the differences across 3 rows. Okay, now if we apply the X derivative filter, the output will still be 3 by 3. What will be the output? What will be the output? Now, don't forget that we need to do flipping, right? We need to do flipping. So after flipping, -1 goes to here and 1 goes to here. So for each row, we compute 20 minus 10, which is 10. And we have 3 rows. So we're gonna sum up. We're gonna sum up 3 3s, which is 30. And the 30 will be divided by 3. So for we get 10 here. Get 10 here. After flipping, -1 goes to here, 1 goes to here. So 20 minus 10 is 10. Because we have 3 rows. So we have they add up to 30. And 30 divided by 1/3, it gives us 10. And similarly, we move this filter across the image. And again, we have 10 here. And if we further slide the filter to this position, okay, and because they are all 20, okay, because this small patch, it has the same value, so there's no difference. There's no difference between neighboring pixels. Clearly, the value is 0. Okay, so we're gonna we just repeat the process, and we end up with a 3 by 3 filter, a 3 by 3 output, like this. Okay, and if we apply the X derivative filter to this input image, and we get this is the the filtered results. This is the filtered image. What can you observe on the result? And similarly, if we apply the Y derivative filter, this is the Y derivative filter to the input image, and you get the corresponding results. Now let's take a closer look at the resulting images and observe the differences. Okay, what can you observe on the result of X derivative and the result of Y derivative? Can you tell the differences? Well, on the result of X derivative, you can observe edges like this. Okay, so you can observe some clear vertical edges, right? But on the result of Y derivative, you may observe this horizontal edges. And look at this place. So the vertical edges appear clearly on the result of X derivative, but it doesn't show clearly on the result of Y derivative. This edge, this part, okay? You don't see it here. So let's compare. Let's compare this part with this part. What's missing? What's missing from this image is that you do not see the vertical edge on the result of Y derivative output, because Y derivative is useful for detecting horizontal edges. So the vertical edges are missing. They're not present from the result, from the output of Y derivative. Okay. And in contrast, you can clearly see this vertical edge from the result of the X derivatives. There's a clear vertical edge here, but not here. And similarly, there's a clear vertical edge here, but not here. Right? And conversely, there's a clear, you can see there's a clear horizontal edge in this position, but it doesn't show on in the result of X derivatives. You don't see the vertical edges very clearly in the result of Y X derivatives. Okay, so the two filters, they are the basic filters for edge detection. This is called X derivative filter, and this is Y derivative filter. So if you want to do edge detection, these are like the first step. The first step for edge detection, just comparing the differences between neighboring pixels horizontally and vertically. So X derivative filter is for comparing the differences horizontally, and the Y derivative is comparing the differences along the vertical direction. Okay, so with those filters, we can now compute the gradient. The gradient is just a vector consisting of X derivative and the Y derivative. Here, we show three images. You can see this is one image. This is another image. Okay. And the red one, the red arrows represent what? Represent the gradient direction and also the gradient magnitude. Well, look at, we have this image. You can see this image. In this image, each column has the same value, right? But along the horizontal position, the image value keeps increasing. The image value keeps increasing for each row. For each row, the image intensity just keeps increasing. But for each column, the pixel values are the same for each column, right? Therefore, the image gradient is represented in this form. The image gradient is non-zero along the horizontal direction. But vertically, it's zero. Vertically, it's zero. It is zero because there's no change in each column. In each column, the pixel value is just the same. Okay? So the Y derivative is zero. The Y derivative is zero for every single pixel. For every place, the Y derivative is just zero. For this place, clearly, at this place, the Y derivative is also zero. Okay? And we are only left with non-zero X derivative. Similarly, for this case, the S derivative is zero. The S derivative is zero because for each row of the image, each row is constant. Each row has a constant value. So the X derivative is zero. For each column, however, the pixel value keeps increasing. So vertically, the image derivative is non-zero vertically. Okay. So for the first two images, their for the first one, their Y derivative is zero. For the second one, their X derivative is zero. Okay. For the last one, you can see the function value keeps increasing following this direction. Okay, it keeps increasing along this direction. And so either along the horizontal direction or along the vertical direction, you can see there's an increase. There's an increase in the function value. So overall, the function value increase most rapidly along this direction. Okay. For the first image, For the first image, the function value increase most rapidly horizontally, because vertically, there's no function value. There's no change of function value. For the second image, the function value increase most rapidly along the vertical direction, whereas along the horizontal direction, there's no change. For the third image, the function value increase most rapidly along the diagonal direction. All right, so what can you observe? The gradient vector points in the direction of most rapid increase in image intensity. How does this relate to the direction of the edge? How does the gradient direction relate to the direction of the edge? For the first image, where is the edge? Where is the edge in the first image? There's only, vertical edges, right? For the second image, there's only horizontal edges. Well, for the third image, the edges are in this direction. So what is the relation? What are their relationship between gradient direction and edge direction? They are what? They are orthogonal. So the direction of the gradient is perpendicular to the direction of edge. Clear? Clear? Because the gradient direction represents the most rapid increase. The gradient vector points, gradient direction points in the direction of most rapid increase, most rapid change in image intensity, most rapid change in image intensity. And remember, when we say edges occur when there's a significant change in image intensity, right? So the gradient direction represents changes along this direction, the most rapid change in this direction. So when there's a rapid change, there's a significant change in this direction, it means there's an edge here. And the edge direction is perpendicular. Edge direction is perpendicular to the changes in pixel values. Clear? Just as we say, if there's a significant change between the two pixels, for example, this is 10 and this is 100. So the change direction, this is the change direction. Okay. Along this direction, the pixel intensity just increased rapidly, and this implies there's an edge here. Okay. So the edge direction, this is an edge. The edge direction is perpendicular to the direction of pixel, the direction of increase in pixel intensity, which is the direction of the gradient. Okay, if there's a significant change, it indicates there's a function, there's an edge present here. Okay. So the edge strength is given by the gradient magnitude. The gradient magnitude computes how rapid the changes is, how significant the changes along the x direction, along the y direction, how significant the changes are. And this represents edge strength. Okay, so if the changes is from 10 to 100, then we have, fx maybe 90. Okay, and this represents a significant change along the horizontal direction. And this represents the edge strength. Okay. Now let's do a small exercise. Now we have this original image, and we apply our x derivative and y derivative. Okay, we apply our x derivative, this x derivative, y derivative to the images. Can you tell which image is the result of x derivative? Which image is the result of x derivative? And which one is the result of the y derivative? This one clearly is what? This is the gradient magnitude map. This is the result of this gradient magnitude. Okay, this is the result of gradient magnitude. And this is the result of x or y derivative. This is the result of x or y derivative. What kind of edges? What kind of edges are more significant within this image? The vertical ones, the vertical edges. So this is the result of what? The result of x derivatives. The result of 1 minus 1, the x derivatives, because the x derivatives are specialized for detecting vertical edges. Okay, and similarly, you can see the vertical lines, the vertical edges are present within this image. Therefore, this has to be the result of y derivatives. Y direction, y derivative. And this is the result of gradient magnitude map. Gradient magnitude. And this image is the computation. This is the result of this one and this one. It's computed by this. Okay, now let's summarize how to do edge detection. Let's take a look at the function intensity with respect to this red line. So this graph is the plot of function intensity along the red line. Okay, this is the graph of function intensity along this red line. Well, as you can see, the intensity value initially are high, and then it go down significantly because these values are black. It go down significantly and it rise up again, and it up and down. Okay, so this is the function intensity value fx. And then let's take the gradient. Let's take the derivative. So this is the f1x. Okay, and you can identify there are several peaks or extremes here and there, and these just represent what? The position of these extremes represent the correspond to the position of what? The position of these extremes correspond to the position of what? Come on. The position of these extremes in the derivatives. In the derivatives, f1s correspond to what? Correspond to the edges, right? Correspond to the edges. The extrema represents the most significant value, the most significant changes in the function intensity. Okay? So the higher of this derivatives means the higher in the changes of f, the function intensity. Okay, so the peaks or extremes in the function derivatives indicate there are significant edges at this position. Okay, so edge detection. For edge detection, what we can do, this is a very simple algorithm for edge detection using image derivatives. So what we can do is to just take the first order derivative and look for the extremes. Okay, we take the absolute value. Remember, at the very beginning of this class, we show you a video about edge detection, remember? This one. And we say, we
So
need
let's
to
look at several orders. In this case, of course,
we say there are two issues to consider. Size of the neighborhood. This is actually, this one corresponds to what kind of filter you use. You can choose backward filter or forward filter or central filter, okay? Well, the second issue is what metric represent a change. Well, this one is about the thresholding. You need to set up a threshold. So we need to set up a threshold, and those with derivative, those with the absolute value in their derivative higher than some threshold is considered as edges. Okay, so pixel with the derivative higher than some threshold.
so let's look again about 76. So all of those.
Okay, so with threshold higher than some threshold, with the differences higher than some threshold, and these pixels are considered edge pixels. On the contrary, so these pixels are not edge pixels because their differences are lower than some threshold. Okay. Okay. So they are not considered edges because their derivatives are just lower than some threshold. Okay. So that's how we do edge detection using image derivatives. Pixels that pass the threshold, so we only these pixels are considered edge pixels. And while the rest of them are not edge pixels because their derivatives are simply below the threshold. Okay. Well, if edge detection is so simple, just that simple, we are done. But in reality, it's not so simple because real images often come with noise. And let's look at, let's consider what happens when there are noise in an image. So if our FX, well, let's consider, for example, this is a clean FX. Okay, this is a noisy FX along this blue line. Okay, so initially, when the images are clean, we have FX like this. Okay, this is the clean. This is the FX for clean image. The pixel intensities are very smooth. They're very smooth. But with noise, you can see there are some small variations in image values. Well, those small variations can be detrimental. The small variations in pixel intensity values that come with the noise. These noises are detrimental because when you take the derivatives, this is the result. When you take the derivatives, you see the problem here, right? Initially, when we have a smooth function, what would be the derivative of this smooth function? The derivative for this smooth function will be like this. Okay, and the peak value for the derivatives here correspond to edge. There's an edge here. Okay, there's an edge here, and this peak value just corresponds to the edge here. Clear? With noises in the function value fx. If you when we take the derivative, there are extremas or peaks everywhere, because the noises just they make nearby pixels. Nearby pixels, initially they have similar values. Initially they have very, very similar values. But with the introduction of noise, the nearby values, they don't have the same values. They don't have very similar values. So if you take, so they have large differences. Nearby pixels, now they have large differences. Okay. So our previous algorithm, this simple algorithm, this simple edge detection algorithm using derivatives, it won't work. It won't work in the presence of noise. Then what do we do? In this case, image derivatives fail. Image derivative fail to indicate significant changes in function values because nearby pixels, they also have very different image intensity values. So what do we do in this case? Well, so far we have learned some smoothing filters. Can we do smoothing first? We apply some smoothing filters to make the image smooth. Okay, maybe we can apply some smoothing filter to smooth the image to make nearby pixels similar again. Well, it turns out that's the idea. The idea is to smoothing the image first. Recognizing this, well, this is a vector, and its function is to smooth. What does this filter do? When you apply this vector, when you apply this one-dimensional filter onto an image, what does this filter do? This filter smooths the function, smooths the image vertically for each column, right? You apply this. How are you going to apply this? You apply this filter to each column of the image, right? And what about this? You apply this to each row of the image, right? You apply this to each column of the image to smooth the function, to smooth the image along the vertical direction. And you apply this to the image, to each row of the image, to smooth each row of the image. And together, this is the result of what? If you multiply this with this, this is the result of the 3x3 filter, right? This is our moving average filter, okay? So in effect, so given an input image I, you can apply this filter to this image. And then you can apply this filter, further apply this filter, which will be equivalent to apply the 3x3 filter to the image. And similarly, we have this vertical one-dimensional Gaussian filter and this horizontal one-dimensional Gaussian filter. The multiplication of the two filters, it gives what? Gives 1, 2, 1, 2, 1, 2, 1, 2. What will be the middle one? 4. Okay. So typically we have 2 smoothing filter. Well, this one is the moving average filter. Of course, there's a normalizing factor 1/9. Okay. So this is the so-called moving average filter. Yet this is the Gaussian filter. What will be the normalizing factor before the Gaussian filter? The normalizing factor should be what? Should be 1 over what? 16, right? Because we can sum up. We just sum up those values, and it gives us 16, 1 over 16. Okay, so typically we have 2 smoothing filter, and the most commonly used one is the Gaussian filter. Gaussian filter is like the standard filter for smoothing. What is the difference between Gaussian filter and the smoothing filter and the moving average filter? You observe that for Gaussian filter, the central value, the central element has the largest weight. The central element has the largest weight, and then the second element weigh most are those 2s. So for Gaussian filter, the weighting of the pixels decrease with respect to what? With respect to its distance to the central. Okay, the weighting of the pixels is inversely proportional to their distances to the central. Clear? Clear? So that's why the central pixel has the largest weight, and then pixels in this position has the second largest weight, because these pixels are closer to central than these pixels. They're closer to central than these pixels. Okay, so the weighting in Gaussian kernel, the weighting of the pixels is inversely proportional to their distance to the central. Okay, this is a typical 3x3 Gaussian filter, while this is a 5x5 Gaussian filter. And you can observe the weight. The largest weight is the central. The weight decrease with respect to the distances to the central. Okay, so for these pixels are the 4 ones. They are most distant to central. Therefore, they have the smallest weight. Okay, and the normalizing factor 273. The 273 is computed by adding up all the numbers. Okay. Well, look at these images. The top one is the input, and the bottom one is the result after applying Gaussian smooth filter. Okay, here the mean filter represents the moving average filter. It represents the all one filter. Okay, This is the Gaussian filter. What is the median filter? What does median filter mean? Well, for median filter, we consider the 9 numbers, and we take the median one. So there are nine numbers here, right? And we represent the filtered, the output. The output is the median of these 9 elements. The output is the median of the 9 elements. This is the median filter. Is median filter linear? Is this a linear filter, just like the moving average filter, the mean filter, Gaussian filter? Are Gaussian filter linear? Gaussian filters, are they linear filters? Mean filter, moving average filter? Well, we already say that the moving average filter is linear. Sharpening filter are also linear. For filters that can be represented in matrix form, in the form of matrices, they are all linear filters. So mean filters are linear. Gaussian filters are also linear. What about median filter? Is it linear or not? Okay. So think about that. And let's take another 10 minutes break. All right. Now let's see if the median filter is linear or not. You know, to see whether a filter is linear or not, a filter is represented. A filter is essentially a function, right? So if it's linear, then it should have this form fx plus y equal to fx plus fy. Okay? Can someone give a counter example? Can you give a counter example that the median filter doesn't give an example that this equality doesn't hold? What is a median filter? Let's consider a simple case. 1, 2, 3. Okay, say we have only 3 elements. Then the median filter should return what? Yeah, the median filter should return 2 because 2 is the median among the 3 numbers. Okay. Then let's say we have another. This is like one image, right? Suppose we have another image, 5, 7, 9. What will be the median filter? The median filter will return 7. Okay. And if we add the 2 image, if we add up the 2 image, if we add them up, the image become 6, 9, 12. And the median filter will return 9. And 9 is the result of 2 plus 7. 2 plus 7, right? Well, it seems it satisfies this equation, right? So is it linear or not? Median filter. Well, we just give you an example. Suppose this is an input image 1 and the median filter returns 2. And this is input image 2 and the median filter returns 7. And if we add them up, if we add the 2 image up, it gives us 6, 9, 12. And the median filter will return 9, which happens to be the summation of 2 and 7. What's wrong? So median filter is linear. Okay, so this is just coincidence. Can you give a counter example? Can you give some counter example that this property doesn't hold for median filter? Okay. Let's ask GPT. Let's try this. Okay. So we have, for example, this image and this image. So median for the X vector, the median filter will return 2. For the second vector, 0, 100, 0, it will return 0. Clear? Right? And if we add up X and Y, it gives 1, 100, 0, and 3. So the median should be 3. And clearly, 3 is not equal to 2 plus 0, which is 2. Clear? So GPT gives a counterexample where we have X image 1, 2, 3. So the median F represent median, Fx is 2. Okay, And for the second image, y equal to 0, 100, 0. The median of the y image is 0. Okay, clear? So x plus y gives this new image, 1, 102, and 3. Well, the median of this new image is 3. And clearly, 3 does not equal to 2 plus 0. Therefore, we have this property. This property does not hold for this counterexample. Okay? Okay, so this is a counterexample provided by GPT. And actually, it gives a lot of examples which shows the equality. The equality holds for examples like this. Okay, but a true counterexample, this is a true counterexample. The last one. Okay. Well, I cannot find that one. Anyway, so if you are stuck with if you lack examples, just try GPT, and it can sometimes it can give you some inspiration. Okay. Anyway, so the median filter, unlike Gaussian and the mean filter, it cannot be expressed in the form of matrix, and it's not a linear filter. But the median filter works really well in some cases. For example, if in the presence of pepper and salt noises, you can see this very noisy image with pepper and salt noise. After applying median filter, the result is pretty good, because you can, by selecting the median value, it effectively remove pepper and salt noise. Okay, now let's back to edge detection. So our solution is to smooth the image first. Smooth the image first. And here we choose Gaussian smoothing. We choose Gaussian smoothing. As we explained, the benefit. What's the benefit of Gaussian smoothing? The benefit of Gaussian smoothing is it assigns weights according to the distance of the pixel to the central. So it assigns larger weights to the central pixel. So if a pixel is closer to the central, then it has more weight than those distant from the central. Okay, so unlike the mean filter, which assign equal weights to each pixel, the Gaussian filter assigns bigger weights to the central and to those near central. Okay, so Gaussian filter, the result of Gaussian filter is more natural, and it places higher importance to the central pixel. So Gaussian filter is commonly used for smoothing because it can better preserve the image content, image value, pixel value. Okay, so we apply the Gaussian filter to the input signal, which is noisy. Okay, and ideally, after applying the Gaussian filter, we have a smooth signal. Ideally, after that, we have a smooth signal, and then we can apply, we can take the derivative. We can take the derivative of the smooth signal, because the signal now becomes smooth, and our our previous idea, the image derivatives just work in this case. Okay, so that's the solution. Given an input signal f, we apply the Gaussian kernel. The Gaussian kernel, this. So this operator represents convolution. We convolve the input signal with G. G represents the Gaussian. We convolve the input signal f with the Gaussian kernel to smooth the function. Okay, so this is the smoothed result. And then we take the derivative filter. This is the derivative filter. And then we can just based on the derivative to identify edges. By looking for peaks in the derivative. Okay. Well, if you look closer, this is our result, right? This is our result. We take the derivative with respect to this is Gaussian. We smooth f with Gaussian. Well, but we have a theorem called derivative theorem. Derivative theorem, it states that this equality, the derivative of f, g convolved with f, is equal to f convolved with g, convolved with the derivative of g. Okay, so we can take the derivative, we can move the derivative inside the convolution. This derivative theorem says that the derivative of the derivative of the convolution is equal to the derivative of Gaussian convolved with f. Okay, so we can move the derivative inside the convolution, meaning that we can take the derivative of Gaussian first and then do the convolution. Okay, we can take the derivative of Gaussian first and then do the convolution. This is given by the derivative theorem of convolution. So the derivative of Gaussian looks like this. This is the derivative of Gaussian. Okay, then we can just simply convolve f with the derivative of Gaussian. You see the difference between Gaussian and derivative of Gaussian. This is Gaussian. This is the Gaussian kernel. Okay, so a typical Gaussian kernel looks like this. This is Gaussian kernel. And this is the derivative of Gaussian kernel. The derivative of Gaussian kernel, you can see there are two extremes. Okay, derivative of Gaussian kernel. We can simply convolve f with the derivative of Gaussian kernel, and you will give us the same results. The same results. Okay. So, given by this theorem, we simply take the derivative of Gaussian and we convolve f with derivative of Gaussian, and we are done. And this is more this is simpler if we know the derivative of Gaussian. This is simpler. This saves us one step. Okay, so for one-dimensional Gaussian filter, this is Gaussian. This is derivative of Gaussian. You can see there are two extremes, right? For two-dimensional Gaussian, this is two-dimensional Gaussian, and this is x derivative of Gaussian. X derivative of Gaussian is convolved, is obtained by convolve the x derivative filter with the Gaussian filter. And you can find two extremes from the results. This is 2D and this is 1D. Okay, this 2D. And similarly, we have y derivative of Gaussian obtained by convolved this with 1, 0, okay, with this vector. And you obtain y derivative of Gaussian like this, y derivative, s derivative. And this is high peak, and this is low extrema, high extrema, low extrema. Okay, so this is x derivative of Gaussian, y derivative of Gaussian, and this is the visualization of the 2D function. Okay. And this gives us, we take the derivative of Gaussian. We take the x derivative of Gaussian and the y derivative of Gaussian. This gives us Sobel operator. Okay, so turns out this is GS. GS represents x derivative of Gaussian. GY represents y derivative of Gaussian. So GS is obtained by Gaussian convolved with this. This is GS. This is GX. Okay, and similarly, GY can be obtained by Gaussian convolved with this one-dimensional vector, and you get GY. All right, then. So we have Sobel operator. Remember, initially we have x derivative filter, y derivative filter, and what do they look like? X derivative filter, remember? X derivative filter. This is the x derivative filter. And this is the y derivative filter. How do they differ from GS and GY? So x derivative filter, 1, 0, minus 1, 1, 0, minus 1, 1, 0, minus 1. Okay, this is the so-called x derivative filter. And we have 1, 0, 1, minus 1, 1, 0, minus 1, 1, 0, minus 1. This is the y derivative filter. You see the difference? The difference is here. Okay? The difference are exactly at this position. For the derivative filter, we have all 1. But for the GS and GY, because it's the derivative of Gaussian. The derivative of Gaussian, well, for Gaussian filter, the weighting is 2 instead of 1. Okay, because of the Gaussian filter assign bigger weights. It assign bigger weights to those closer to the central. So can you see the difference between the Sobel operator, which is the derivative of Gaussian, and the top one represent the image derivative filter. So it's just 1 minus 1, 1 minus 1. Okay, it's different from derivative of Gaussian, where the weights here are 2 instead of 1, because it's the derivative of Gaussian instead of derivatives only. Okay, so Sobel operators are the most commonly used edge filters, the most commonly used edge filters. What are the advantages of a Sobel operator compared to the X derivative and the Y derivatives, compared to the normal image filters? What are the advantages of Sobel compared to normal image filters? As we explained, GS-GY is the derivative of Gaussian filter, and Gaussian filter can be used to smooth the image, reduce noise. Okay, so GS-GY compared to the ordinary image derivatives, GS and GY have the effect of noise reducing, smoothing. Okay. And once we have GS and GY, we can of course compute the magnitude of the image and also the direction of the gradient. Okay. So this is an example of applying Sobel filter. So for this image, this is the result of what? You see a lot of horizontal edges. So this is the result of what? This is the result of applying GS or GY. This is the result of applying GY. And this is the result of applying GS. Because there are a lot of vertical edges in this. And this is the gradient magnitude map. Okay. How do we obtain the edges? How to obtain the edges? Once we have this gradient map, what should we do? We should threshold the gradient map. And those, you see the pixels, the Y pixels they have higher gradient values, gradient magnitudes. They have higher gradient magnitudes. And those are likely to be the edges if we're thresholding them. Okay, if we're thresholding them. Okay, so normally, that's the result we get. We have a gradient magnitude map, and then we set some threshold. Okay, if we use a very high threshold, we get many discontinuity edges. So those edges are discontinued, and there are some missing pixels. This is our edge map. If we apply a high threshold, if we apply a low threshold, if we apply a low threshold, you can see the edges become continuous. However, it also introduces some too many details. It also introduce some unwanted edge pixels. Okay, so that's the result. That's some typical results. If we just simply threshold the gradient map, if we threshold the gradient map using a threshold, so it's difficult to choose a proper threshold. If you set a threshold too low, it retain too many details. If you set the threshold too high, it might only retain some a few edges, and the edges become discontinued. The problem with Sobel filter is greater than that. Okay, it's greater than that. Well, first of all, we can see that Sobel filter tend to work in this case. It tend to work in this case. You know, when there's a step edge, in this case, such an edge can be detected. It can be detected using a threshold, right? But what about edges like this and edges like this? You know, the edge values change gradually. The edge values change gradually instead of abruptly. Okay, so in this case, Sobel filters will trigger, because the edge value change gradually, it will trigger multiple response. It will trigger multiple response. You will trigger multiple response in this case. So you will have poor localization. You will have multiple response like this, and also poor localization. Let's take a look at example. So what do we mean multiple response? For example, this is a close-up. This is the close-up of this red rectangle. Red rectangle. Okay, and you can, this is the gradient map. Well, you can see there are multiple response. So this is not a thin edge, because it trigger multiple response. This is not a thin edge, and what we want is a thin edge. This is a thick edge, because it trigger multiple response. And it happens. This happens when image pixels, when the edges, they do not appear abruptly, yet they change gradually. Okay, so to address this issue, Canny edge detector, which is probably the most popular edge detector, named after Jay Canny, named after the author of this paper. Okay, so Canny edge detector. Let's go to this. 45 years of boundary detection, 45 years of edge detection. And this is the Sobel edge detector proposed in 1968. This is Sobel. This is Sobel. And where's Kenny? Kenny is the blue one. This is Kenny edge detector. Okay, so Kenny edge detector performs much better than Sobel. And Kenny is proposed 1986, blue one. This one, this is Kenny. Okay. And this represents human performance. Anyway, so Kenny edge detector is like the most popular detector. And the first two steps of Kenny is exactly the same as Sobel. Okay, so the first two steps is essentially equivalent to Sobel, because you just use derivative of Gaussian. So in the following, we're gonna show you how you adjust the multiple response problem. Well, that's the first innovation. You called non-maximum suppression. Because the Sobel operator, as we explained before, it can trigger multiple response. It leads to thick edges. So non-maximum suppression is to make those thick edges become thin edges, and a process called thinning. Okay, thinning. And the second one, as we showed before, how to do thresholding. In Sobel, it's difficult to choose a proper threshold, because if the threshold is too low, it retains too many detail. If the threshold is too high, it makes the edges discontinue. So the second innovation in Kenny is to use a new thresholding method, which introduces two thresholds instead of one threshold, okay, to address this issue. Now let's take a look at the first one, how to do thinning. These are the derivative of Gaussian filter we have seen, okay? And then we compute the gradient map. This is the problem. This is the thick edge problem or multiple response problem. Okay. Now how can we do thinning or non-maximum suppression? We can do it in two different ways. One is that remember when we say the edge direction is perpendicular. This is an edge. The edge direction is perpendicular to what? Perpendicular to the direction of gradient. Okay? So edge occurs when gradient reaches a maximum. So if there's an edge here, the gradient should be maximum. Okay? And within an image, there are only 8 angle directions. Okay? What we mean is that given an image like this, we only have 1, this is 1, 2, 3, 4, 5, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. Right? We have only 8 directions. We have only 8 directions within an image, right? Okay, so only 8 angle directions possible. Now, this represents the gradient direction, and this is the edge direction, okay? Previously, in this case, this is the edge direction. The red one represents edges, right? And we have this. This is our this is the gradient. This is the gradient direction. Okay. So if we want to do non-maximum suppression, we want to along the gradient direction. We want to preserve. We only want to keep among the three edges. We only want to keep the one that has the largest gradient value. So if the middle one has the largest gradient value, then we keep it. If the middle one, the gradient of the middle one is bigger than its two neighbors. If it's bigger than its two neighbors, then we keep it. Otherwise, we discard it. Okay, so we are comparing along this gradient direction. We are comparing this value with this value and this value. So if the gradient of the current pixel, is bigger than its neighboring, it's bigger than the gradient to its left, and it's also bigger than the gradient to its right. Okay, if it's the case, then we keep the gradient magnitude. We keep the gradient magnitude of this pixel. Otherwise, if its gradient is lower than this, then we set its gradient to be 0. Clear? So how can we remove redundant gradients? Well, first of all, you should note it. There are three edges here because this is the gradient direction. There are 3 edges here because they all have large gradient values, right? They all have large gradient values. So in non-maximum suppression, we want to remove spurious gradients. We want to remove redundant gradients. Let's say if this one is the highest among the 3, if it's the highest among the 3 gradients, we keep it. Okay? And likewise, because this one, the value of this one is lower than this one, it should be set to 0. And similarly, the value of this one is lower than this one, so its gradient will also be set to 0. Okay, then finally, we're only left with the middle one because it's the highest. It has the highest gradient value. So that is how we do non-maximum suppression. Okay? So I'm going to say it again. Let's say the gradient value of the 3 points are 100, okay, 198 and 97. Okay, so their gradient values, they're all big. They're all big. That's why we have those redundant gradients. But now we want to do non-maximum suppression. We only want to keep the highest one. The middle one will be kept because the middle one for the middle pixel, its value is larger than its neighbors. 100 is larger than 98. And 100 is also larger than 97. So the value of this pixel, the gradient of this pixel will be retained as 100. Okay? However, for this pixel, because 97 is lower than 100. 97 is lower than 100. It doesn't satisfy this constraint. So its value will be set to 0. And similarly, for this point, because 98 is lower than 100, it's lower than its neighboring pixel. So its value, gradient value, will also be set to be 0. So that's how we do non-maximum suppression. Okay, so we mentioned that we can do the suppression along the real angle direction. That is the rounded gradient direction. The rounded gradient direction, that is, for example, at this point. So the current pixel is Q, okay? The current pixel Q, this is the current pixel. And this is the real gradient direction. This is the real gradient direction. This is the gradient direction we computed. Remember, we have this ds dy. Okay, and this direction is computed by the arctangent dy ds. Arctangent dy ds. So this is the real gradient direction. But as we said, within an image, they are only a direction. So we are going to round this. We are going to round this direction to its nearest, the rounded gradient direction. Okay. So we are going to round the yellow, the real direction, to its closest, the closest angle direction, which may be this one. This is its closest angle direction. Okay, and then we do non-maximum suppression along. We do non-maximum suppression along this rounded angle direction. And along this angle direction, we are going to consider the gradient of this point and the gradient of this point and this point to determine whether we keep its gradient or not by comparing the 3 pixels, the gradient value of the 3 pixels. Okay, so that's one way. That's one way to do non-maximum suppression, suppress all pixels in the rounded gradient direction. The gradient direction is not its real gradient direction, but it's rounded. It's the closest. It's represented by the yellow, blue one, which is the closest angle direction. Okay, so that's one way. That's one way to do non-Masterman suppression along the closest angle direction. But we can also do non-Masterman suppression along the real gradient direction. This is the real gradient direction. This is the real gradient direction. But how can we compute the real gradient direction? If we decide to do non-Masterman suppression along the real gradient direction, we are comparing this point. We're comparing this point and this point and this point, right? But the 2 points, they are not real pixels. They're not real pixels within an image, right? They're not real pixels. So in this case, we should do interpolation. We are going to compute the gradient of this non-real pixel. This is not a real pixel. So we are going to compute its gradient using the gradient of the two neighboring pixels. It's called interpolation. Okay, and similarly, the gradient of this pixel, of this non-real pixel, can be computed using interpolation, by doing interpolation of the two pixels. Okay, so that's the idea. We can either perform non-Masterman suppression along the rounded gradient direction. Along the rounded gradient direction. The blue one, sorry. Along the rounded gradient direction. Okay? Along the rounded gradient direction and comparing the gradients of the real pixels. Or we can do non-Masterman suppression along the real gradient direction represented by the yellow one. And in this case, we need to do interpolation to compute the gradient of those non-real pixels. This non-real pixels. We need to do interpolation to compute their gradient values, so we can comparing the gradient of the three gradients. Okay, so that's how we do non-Masterman suppression. And let's take a look at the results. That's the before non-Masterman suppression. You can see there are many thick edges. Okay, and that's the result of after non-Masterman suppression. And you can see the edges become thin. There's only single edges. So non-Masterman suppression is really important to obtain a good quality edge map. Okay. The second innovation in Canny edge detector is to use two thresholds instead of only one threshold to avoid streaking, to avoid discontinuity. And we will introduce this one in next week. Okay, so that's all for today, and see you next week.